In this video, we'll take a look at converting a series of two branches of a resistor in series with a reactive component to two parallel branches, a resistor in parallel with a reactive component. If we're going to do that, what we'll see is we need to consider the quality factor of the simple combination. So let's take a look at doing that. When we do that, remembering the quality factor of branches in series, that's the series reactance, the magnitude of the series reactance, so we drop the J, divided by the resistance. Where in parallel, that's the resistance divided by the magnitude of the parallel reactance. If we remember in that last video, we looked at this circuit. We tried to convert it to a parallel RLC, and we came up with a 16% error. We solved for our omega naught, where the admittance was entirely real, to be at 2 radians per second. That is 60% error from the maximum input admittance. But if we look at the quality factor of this series branch, that's only 1. If we look at the quality factor of these parallel branches, that's only 0.75. If you remember, a high Q circuit has a Q of greater than or equal to 5. So we don't have a high Q circuit. In order to make a good transformation to a parallel or series RLC from this, we would need to have quality factors greater than or equal to 5 for our approximations to not have this error in it. So to convert to a series or parallel, we need to get a relationship then between our series resistance and parallel resistance, between our series reactance and parallel reactance in order to do the conversion. So just like we did in the last video, we'll equate the admittance. So we're equating admittance in we could equate admittance or impedance. It's easier to find the impedance of series branches, easier to find admittance of parallel branches, but we'll look at equating the admittance. So if we look at the admittance of the series branch, we got 1 over Rs plus JXS. We need to get a real denominator here, so we'll multiply the numerator and denominator by the complex conjugate, and we end up with a real part of Rs over Rs squared plus x squared, an imaginary part of negative xs over Rs squared plus xs squared. It's easy to find the parallel admittance. We just sum the two branches. We get 1 over Rp plus 1 over our JXP. In parallel. So we get our 1 over Rp minus J1 over XP, same thing. But so this is what we need to set equal to. If we set Ys equal to Yxp, then we can find a relationship between the resistances and the reactances. So our Ys then, setting these equal, what we're essentially saying is Rs over Rs squared plus x squared is 1 over Rp, and Xs over Xs squared plus Rs squared is equal to 1 over Xp. So we can solve for our if we're converting from series to parallel, this would be our parallel resistance. It would be a combination of the square of the real part and the magnitude of the reactance divided by the resistance, and then it's similar to get the reactance, except for we divide by the series reactance. So we can get that exactly. If we take these two equations and we divide the two expressions, we can get a relationship that Rp over Xp is equal to Xs over Rs. So our resistance in parallel divided by our reactance in parallel is equal to our reactance in series divided by our resistance in series. And if you recall that our quality factor, that's omega naught Rc, is also equal to Rp over Xp, and our in parallel and in series it's Xs over Rs. Essentially what we've done is we've set the quality factors equal for the two circuits. So that's the relationship with quality factor. It is, resonant circuits, quality factor is one of the most important characteristics that we try to keep track of. So if we we put our transformations in terms of the quality factor, then with this little bit of algebra, we can solve that Rp, the parallel resistance, is actually the series resistance times 1 plus that quality factor squared. And our parallel reactance is the series reactance times 1 plus 1 over that quality factor squared. So, and it's the reactive terms that if we take a look at here, if this quality factor is greater than or equal to 5, that's going to be, even if it's equal to 5, that's 1 over 25 there. So that's much smaller than just this 1. So we can say that our parallel reactance is approximately equal to our series reactance for a high Q approximation. So our parallel capacitance would be approximately equal to the series capacitance, and the parallel inductance approximately equal to the series inductance. So that's nice. They don't change at all. What happens to the resistances, they do change. So the parallel resistance, if we're converting from series to parallel, the parallel resistance will be that series resistance times that quality factor squared. So it's going to increase, and that makes sense. And the series resistance is going to decrease by a factor of 1 over Q squared based on what that parallel resistance is. We know that in series, the higher the resistance, that's representing the loss, and in parallel, because the current's got to flow through that in series. In parallel, if the current doesn't flow through the resistance, then you don't get the loss. So we want to increase that resistor. So that's how these approximations work for high Q. So in a high Q circuit, it's pretty easy to change from a non-resonant form to a resonant form RLC by looking at series branches and parallel branches and deciding which way to convert. So let's take an example of taking a series arm of a 5 ohm resistor in series with a 100 millihenry inductor. The details of the rest of the network aren't available, but we know we're interested in 1000 radians per second, and we want to convert this to a parallel combination. So essentially, we have this series combination. We have everything else in parallel. So this is the part we want to convert to a parallel combination. So our frequency, our resistance, our reactance then is omega times L, so it's going to be 100 ohms, and our quality factor in series, XS over RS, is going to be equal to 20. So that definitely qualifies as high Q, so we should be able to use our high Q approximations. So using our high Q approximations then, we get that parallel resistance, Q squared times RS, that's going to be 20 squared, 400 times this 5 ohms. So that's our 2 kilo ohms. And our XP, that's just going to, is going to approximately equal to XS. So that inductance in parallel is going to be equal to 100 millihenries. So that's not going to change. So we can go ahead and we can compare this impedance looking in series to this impedance looking in parallel. And when we do that, again, we get our impedance in series. That's just 5 plus J100. So that's converting that to polar form. That's 100.1 angle 87.1 degrees, right? The inductance J100, that's much greater than the 5, so our angle is closer to the 90 degrees, and it's approximately equal to a magnitude of 100. If we compare that to in parallel we have we'd have to have 2000 times J100 divided by 2000 plus J100. We calculate that, we end up with 99.9 angle 87.1. So that's only a 0.2% error. So both of these circuits have a quality factor of 20, and when we convert them, the impedance of the two branches, whether in series or in parallel, are just a 2% error. If we look off of, so that's true at our radian frequency of 1000, where we calculated the transformation with a radian frequency of 1000. If we look off of that by a factor of 10% there and just look at J900, we get 5 plus J90 or 90.1 angle 86.8, and for the parallel we get 2000 times J90 over 2000 plus J90. That's our 89.9. So we're still within, with a very small percentage error, within less than 1% error, even 10% off the resonant frequency. So that's an example of the transformation. We'll look further at this in other videos.